Welcome back. So things are getting pretty interesting now. We feel pretty comfortable with solving linear systems of differential equations x dot equals ax by decomposing this into its eigenvalues and its eigenvectors and solving the system. And we've seen some examples, some 2D examples where we have unstable eigenvalues, some where we have stable eigenvalues, some where we have one unstable and one stable saddle points, and also systems where we have complex conjugate eigenvalues, systems that kind of oscillate or rotate in time. But most of the real world is not linear. Most of the real world is not, small angle approximations of a pendulum and things like that. Most of the real world is actually nonlinear. When you think about Newton's law of gravitation and planetary dynamics, or an actual pendulum has, it's not theta double dot equals theta or minus theta, it's minus sine of theta. There's nonlinear terms. And so what we're going to talk about is how to analyze honest to goodness, fully nonlinear differential equations that are really nasty by finding fixed points and linearizing, zooming in near that fixed point where it looks approximately like this system, where we have tools where we can analyze that system. So this is one of my favorites. This is really a big step transitioning from kind of intro, simple, linear ordinary differential equations to starting to build the framework and the scaffolding and the architecture for solving this, much, much richer class of very nonlinear systems. So specifically, this is called linearizing or linearization, linearizing a nonlinear system at a fixed point. So I'm going to define all of these terms at a fixed point. And one of the reasons that nonlinear systems are difficult is because linear superposition doesn't necessarily hold up here for a nonlinear system. I can't take different solutions and add them up and expect them to still be a solution like I can with these linear systems. So we need fundamentally different techniques to solve these. So what we're going to do is start with a generic nonlinear system, x dot equals f of x. And I think I'm going to drop the under bar. Just assume that these are vector systems. These are, x is a vector of states, and this is a system of differential equations. Remember earlier, x could have been the populations of bunnies and wolves and cats and dogs and tigers and whatever, like a bunch of animals. And it was linear and diagonal and decoupled if they were all in different compartments in a zoo. But if I have them in the wild, in the wilderness, now those animals are eating each other and doing all kinds of, there's interactions, and those often manifest as nonlinear terms. So for example, the number of bunnies that get eaten by wolves is not just proportional to the number of bunnies, it's proportional to the number of bunnies times the number of wolves. That's a nonlinear term in this differential equation, okay? So x dot equals f of x, we're gonna say that this has a fixed point. X bar is a fixed point. Literally means that it stays put, it stays fixed at that point. If you start at x bar, you stay fixed at that point. Is a fixed point if my function f evaluated at x bar equals 0. That's kind of a funky f, sorry, it looks weird. That's an f. If my function evaluated at x bar equals 0, then that means that ddt of x is 0 at that point, meaning that it doesn't change in time. There's no dx dt because f of x bar equals 0. So if I start at this point, I stay at this point because it's fixed, because there's no change in time from that point. Good, and so kind of in a word, ddt of x bar would be 0. Okay, and so what linearization does is that we zoom into a neighborhood near that fixed point. So I'll draw like a little picture here. I'm actually going to show you this example later where in 2 dimensions, maybe I have some dynamics that look, like this. And I'm trying to think of how to actually draw this. Maybe I have some system that looks like like this. So I've got all this nonlinear stuff. I've got, you know, lots of trajectories in this system, but I have a couple of fixed points. I've got one of them here, and I've got one of them here, so that if I started exactly near that fixed point or exactly near that fixed point, I would stay put there forever. Okay, and so what we're going to do is we're going to zoom in on one of these fixed points. We're going to zoom in on a little teeny window around here, or a little teeny window around here, and we're going to pretend that nothing else exists. We're just going to zoom into this little neighborhood around these fixed points, and in that little neighborhood, they're going to look like linear systems that we know how to analyze. So so this is a fixed point, and now what we're going to do is we're going to say for some point x that is near that fixed point, nearby to that fixed point. So basically we're going to say that x equals x bar plus a little delta x, where delta x is small. So you know, delta x equals x minus x bar is small. And so I'm just going to keep going back to this little picture to help orient myself. So if I'm at this little point, you know, this is my point x, and this is my point x bar. And this little difference between them, this little delta x here, this little delta x distance, that's a small distance because we've zoomed into a small neighborhood. For x near x bar, meaning that it's a little small delta x apart, then we can Taylor expand this differential equation. This is where it gets interesting. We can Taylor expand this differential equation, and we get, how do I want to write this? So I want dx dt equals f of x. Good. So I'm just convincing myself that this is true. So, so x dot is, of course, going to equal f of x. That equals f of x. And that is going to equal f of x bar plus delta x. And because delta x is small, I can Taylor expand at this base point x bar, at my fixed point, in powers of delta x. And so that's pretty easy. That's going to equal f at x bar plus the derivative of f with respect to x. And because x is a vector, and f presumably has multiple components also, this is literally, you know, let's say x1, x2, dot, 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 xn, ddt of that equals, then this f also has components. It has f1, f2, dot, 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 fn, and these are all functions of, you know, x1, x2, dot, 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 x1, x2, dot, 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 x1, x2, dot, dot, dot. This is literally a vector valued function, right? There's like components to this function f, one for the x1 dot equation, one for the x2 dot equation, one for the x3 dot, and so on and so forth. When I compute the derivative of f with respect to x, this is actually a matrix derivative called a Jacobian. And so usually we write it with a big capital D f dx instead of little d f little dx. This is big df big dx because that means I'm going to take a matrix of derivatives. I'll show you what this means in a minute, but it's a matrix of partial f1 partial x1, partial f1 partial x2, partial f2 partial x1, and so on and so forth. So this is a matrix of derivatives that I evaluate at x bar times, this is literally a dot product because this is a matrix, dotted with delta x. I don't even need parentheses here. Dotted with delta x. Because delta x is also a vector. This is like a vector, delta x. That's the first term in my Taylor series, plus the second Jacobian derivative, the second matrix derivative of f with respect to x squared, evaluated at x bar, again dotted with delta x squared, plus, you know, cubic, quartic, and so on, plus dot, 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 forever and ever and ever. And sometimes we just say plus higher order terms. Okay, this goes on and on, or, you know, plus order delta x cubed and higher. Okay, that's another way to write it. So this is the Taylor expansion of my dynamics, my nonlinear dynamics, zoomed in around a fixed point x bar, where I'm only kind of a little delta x away from that fixed point. And so the key observation here is that all of these terms are very small, very small, very, very small if delta x is small. So if delta x is small, then delta x squared is tiny, and delta x cubed is minuscule, and delta x to the fourth might not even be there, might as well. And all of these terms kind of are approximately 0. And so you get a very good approximation of the dynamics with this term here. And then the last piece is, of course, f of x bar is equal to 0. So this is kind of the only term that's left in the dynamics when these are small and this is 0. Okay? And so what we have is that basically, and of course x here, so we get basically x dot is really d dt of x bar plus delta x, but x bar is just a number. It's like it's a constant vector at that fixed point. And so really this is like d dt of my delta x. So delta x is kind of the new state of my system zoomed in here, little delta x. d dt of delta x equals this Jacobian matrix df dx evaluated at x bar times delta x. And I claim that this is going to be a linear ordinary differential equation, linear ODE, in delta x. And now I'm going to show you how to compute these df dx's, what these mean, and why this is linear. Okay, good. So this was a big step. Now what I'm going to do is I'm going to show you how to compute these matrix derivatives. Maybe I'll just do it for a 2x2 f vector field because it'll be a lot easier, but it's very, very simple to generalize this for an arbitrary n degree of freedom system, you know, a vector where x has n elements. Okay, so good. I'm going to write that out for you just so that you see. So, and I think I'm actually going to write it right here. So this df dx, and you know what, I'm actually going to write it in general because I want to. Okay, I'm going to write it in general, and then I'm going to give you a 2D example, like an actual f of x in 2D like this, and we're actually going to pick a fixed point and linearize. So that's how I'm going to end this. So df dx for an arbitrary, you know, n degree of freedom system is going to be a matrix of partial derivatives. It is going to have partial f1 with respect to x1, partial f1 with respect to x2, dot, 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 partial f1 with respect to xn. Okay, that's the first row of this thing. The next row, as you may have guessed, is partial f2, the second row, partial x1, partial f2, partial x2, dot, 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 partial f2, partial xn, and then, you know, dot, 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 every row is the same. And then the last row is partial fn, partial x1, partial fn, partial x2, dot, 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 partial fn, partial xn. And that is literally my matrix of partial derivatives. This is df dx. This is called the Jacobian matrix. Very, very important. And here these are all functions now. These were functions, and so their derivatives are functions. And here we're going to evaluate this. This is a matrix of functions. Here we're going to evaluate this at our fixed point x bar, and this is going to turn into a matrix of numbers. These are all going to be numbers when I plug in x bar into all of these equations. Okay, so that's what I mean by df dx. This is literally a matrix, and that's why this is a linear ODE, because it looks like x dot equals ax, with this being the A matrix. Okay, good. I am going to erase some stuff, and then we're going to write down a two-dimensional example and solve it. I wish erasing that was as easy in real life. Okay, so the example we're going to do, this is a really simple example, and I'm going to actually in the next few lectures build up a bunch of examples, some of my favorite examples from Newton's second law, F equals ma. We're going to look at potential systems where we literally take like some potential function and we put like a bead, on that potential function and watch it move. We're going to do a bunch of examples. So in this one, what we're going to have is f of x, and remember f is a vector and x is a vector. And of course, that's f1 of x1, x2, f2 of x1, x2. And I'm specifically going to define these two functions to be x1 minus x1 squared and x1 plus x2. These are my f1 function and f2 function. I've chosen them to be easy on purpose because I want to make my life easy for this kind of introductory warm-up example. And for this example, you can read these fixed points off really easily. So there are two fixed points of the system where both of these equations are equal to 0. So in the top equation, x1, basically x1 can equal 0, or x1 can equal 1. And if x1 equals 0, then x2 has to equal 0. That's a fixed point. And if x1 equals 1, then x2 equals minus 1. So we basically have a fixed point. The fixed points x bar are 0, 0, and x bar equals 1, minus 1. These are the two fixed points in phase space. I always call phase space the space of x1 and x2. That's just an old habit. Okay, so the way that we basically linearize, so we want to zoom in to a small neighborhood of these two fixed points, and in that small neighborhood, they're going to look linear. This nasty nonlinear system, away from these points, all bets are off. But if I zoom in really close to the origin or really close to this point 1, minus 1, the dynamics are approximately going to be linear according to that formula I wrote down before. And so I literally just have to write down this Jacobian matrix df dx, and that's my matrix of partial f1, partial x1, partial f1, partial x2, partial f2, partial x1, partial f2, partial x2. I'm getting a little sloppy, you can see, but it's really easy to compute these partials. So the partial of f1 with respect to x1 is 1 minus 2x1. The partial of f1 with respect to x2 is 0, because this has no x2s in it. The partial of f2 with respect to x1 is 1. That's really simple. And the partial of f2 with respect to x2 is also 1. That's really simple. So this is the Jacobian matrix in general. And now we have to evaluate this Jacobian matrix at these two fixed points to figure out what our A matrix is in those neighborhoods. Okay, so fixed point 1, let's say fixed point 1. Is, let's say, x bar equals 0, 0, x bar equals 0, 0. And so here what we have is df dx evaluated at x bar. We literally take x1 equals 0, x2 equals 0, and we plug it in here. And this matrix, anytime I see an x1 or an x2, they're equal to 0. So this matrix becomes 1, 0, 1, 1. That is the A matrix for my linearization zoomed in at this 0, 0 point. And we can do things like compute its eigenvalues. If I read these eigenvalues off, the lambdas are +1 and +1. Any matrix that has zeros either above or below the diagonal, then the diagonal elements are going to be the eigenvalues. That's really easy to show. That's a good homework problem for you. And so the lambdas equals 1, 1, so this one is unstable. It's like an unstable source. Okay, good. So that fixed point, things are going to emanate away from it locally in an unstable way. Let's look at my next fixed point. Maybe I'll do this one in orange. So fixed point 2, x bar equals, what was it, 1 minus 1. Again, I'm going to compute df dx. evaluate it at x bar, literally meaning I plug in 1 for x1 and -1 for x2, but there are no x2s here. So this Jacobian matrix is now 1 minus 2 is -1, 0, 1, 1. This is more interesting. Now my eigenvalues are going to be saddle points. So I have one stable, one lambda is +1 and one lambda is -1, so I get lambda plus or -1. So this is a saddle point, okay? Which is kind of cool. And if I wanted to figure out what directions were stable and unstable, I'd find the eigenvectors of this. If I wanted to know the eigenvectors corresponding to the stable and unstable directions, I'd find its eigenvectors, similar for this. And I haven't done this in my notes, so I'm a little nervous about it, but I think it should be fine. So now if I look in my x1, x2 plane, my phase plane, I have a fixed point, 0, 0 right here, this fixed point right here, and I have another fixed point at 1, -1, 1, -1 down here. And we know that locally, zoomed in locally to this point, 0, 0, my dynamics are unstable. It's an unstable source. And because these eigenvalues are equal, I'm assuming it kind of is just like unstable, the same magnitude in every direction, kind of like this. That is what this point locally linearly looks like. And this point is going to be a saddle point, okay? And so that point locally linear, I don't know what directions are going to be stable and unstable, but it probably is going to have something like this where these guys are locally stable and these guys are locally unstable, and things kind of, I hope I drew this right, things kind of go in this orientation. And who knows what happens between these? Probably something catastrophic. I'm assuming what happens is that maybe there's some behavior here where these two meet. I don't know. That's something we'll talk about in another day, is how do you interpolate or infer what happens between these fixed points. With this linear analysis, all that we can say is that there are these fixed points, and if we zoom into a really small neighborhood, they behave linearly like x dot equals ax, according to these Jacobian A matrices. Okay, so pretty cool that you can really start to analyze really nasty systems using these linear techniques that I showed you before. And one of the ones I love doing, I'll show you this in another video, you can have things like, I have a saddle point here, and maybe I have a spiral sink here. And so I can do things like infer, well, probably this will connect to that, and you can actually start to complete this kind of global phase portrait. You can start piecing together kind of globally what's going to happen in some of these nonlinear systems based on these rules and these linearizations. Okay, that's all coming up soon, so thank you very much.